In the name of Almighty God, I am Hassa Sankashi, and today I want to talk about non-clustering of baryonic matter. Before considering dark matter, let us first focus on the case of baryonic matter coupled to photons. This means that the protons as well as nuclei and the electrons, which in cosmology are collectively called the baryonic matter, are tightly coupled by the electromagnetism to the photons. They form a matter fluid with a relativistic sound speed when the nuance is almost equal to the c divided by square root of 3, where c is 1 is the speed of light, and with this extra input from the relativistic physics, we can then proceed with the non-relativistic Jeans equation for density perturbations based on the equation 1.14. The large speed of sound, nu s, is almost equal to omicron 1, means that the large pressure provided by photons dominates over the gravitational terms in equation 1.14. One does expect that such a fluid doesn't cluster. This is confirmed by the explicit solutions of equation 1.14 in a matter-dominated universe. For example, in the case most favorable for clustering, since radiation doesn't cluster, one has rho 0 is equal to, or the first density is equal to 3 multiplied by Hubble max Planck expansion to the power of 2 divided by 8 for Pg it is equal to 3 divided by 2 th0 to the power of 2 divided by 3, and h is equal to upring to divided by r is equal to 2 divided by 3t. See the appendix C, for example, equation 1.14. Then becomes the second derivative of the delta k based on the time plus 4 divided by 3t multiplied by delta or derivative of delta k based on the t plus nu s to the power of 2 k to the power of 2 divided by 3 divided by 2 h0 to the power of 4 divided by 3 t to the power of 4 divided by 3 delta k is equal to 0, which after simplification we have delta k is equal to c1 cosinus c0 cot t to the power of 1 divided by 3 plus c2 sinuside c0 cot t to the power of 1 divided by 3 divided by cot t due to the power of 1 divided by 3. For simplicity, we don't specify the coefficients c0, c1, and c2, which depends on the nuance and h0. The main result is that this solution is oscillating pressure waves observed as peaks in the CMB power spectrum. And what is the actual CMB? Actually, the CMB is a cosmic microwave background, and I want to spell it here that CMB is equal to cosmic microwave background. So it means that the residual radiation from the Big Bang, and originally it's during the recombination of the epoch, and this epoch is almost equal to 380 kilo years. So this is the originated during recombinated from the epoch after Big Bang. After universe cooled, the proton and electron combine to the neutral hydrogen atom. It means that the first things we have the cooling. This is the universe. The first time, and the T is equal to 0. We have a hot and dense plasma. It's not just the dense as a three popular uh, It wasn't the three material phase such as solid, liquid, and gases. We had at the T was equal to zero. After Big Bang, the universe was actually very hot and was equal to the dense plasma. After it gets cooled in T was more than zero, and the T were much more than the zero. We have the such universe was cooled, and this cooled was concluded that the proton and electron combined together, and they eventually we had the hydrogen as a neutral hydrogen atom. So a photon, a constantly scattered charged particle, it's a fundamental of the features of the photons. So photons scatter the charged particle, and these charged particles made the universe very opaque. And after that, these charged particles were the seeds of the universe, and the seeds formation of the galaxy. Radiation was isotropic, and isotropic this radiation that the photons has at the universe when the time was equal to zero. This sort of radiation was actually isotropic isotropic. So this sort of isotropic, the iso it's a Greek it's a combination of Greek, and iso is a equal and tropic is away. So it was radiating to all direction. The opposite of the isotropic is actually anisotropic, and anisotropic is just radiating from the one direction. So when we are talking about the photons that happens here, the next things that I want to talk about is the actually Bremsstrahlung. Bremsstrahlung. It's actually such as the photons, but the only difference it is also the radiation, but this radiation is actually anisotropic and it has the one direction. So it is anisotropic, but this is the isotropic. So the cosmic microwave is the actual residual radiation from the Big Bang, and this residual radiation was hot and dense plasma, and this was actually plasma, and we didn't have the other popular of the material phase. It wasn't at that time the transition to the solid or liquid or gas. We just had a plasma. So after that, after the universe got cold, the proton and electron combine together to make a neutral hydrogen atom. Before this cooling happened, when we had a hot and dense plasma, we had the photons, which travels to the universe as isotropic. Isotropic, as I told you, is whenever you are encountering to this phrase, isotropic is it has two separate sections. It's a Greek phrase. Iso is equal and tropic is away, and it means that it's a scattering through all directions. And the opposite of the cosmic microwave background, we have a Bremsstrahlung radiation, and I will reach it later. So come back to the rest of the lecture. We were there here, CMB power spectrum and damped into time. At this moment, you know that what is the CMB? Whenever we are calling in this literature CMB, cosmic microwave background, it means that we had at that time photons scattering to all directions. And damped in time, the baryonic tightly coupled fluid doesn't cluster on scales when Ka was larger than Kj. A was equal to A multiplied by H divided by nu s, with the latter equal to the horizon, given that nu s is equal to omicron 1. In other words, normal matter without dark matter only clusters at a late time after it decouples from photons. Now I want to go through the clustering of dark matter. What makes cold dark matter different is that it doesn't interact with photons and is collectively described by a simple fluid with a non-relativistic sound speed nu was equal to zero. This makes a huge difference in cosmology, keeping only the gravity term in equation 1.14 and considering again the matter-dominated phase of the universe. One obtained the second derivative of delta k based on the time plus 4 divided by 3t multiplied by derivative delta k based on the time minus 2 divided by 3t to the power of 2 delta k is equal to 0, giving the delta k is equal to c grow multiplied by t to the power of 2 divided by 3 plus c decay t to the power of minus 1. This solution contains a decaying mode that dies off and, most importantly, contains a mode that grows with a specific positive power of time. This is how the universe evolved from a primordial quasi-homogeneous state, which delta k is almost equal to 10 to the power of minus 5 to the present clumpy state. Incidentally, Incidentally, note that the exponential growth found in the static case has become a parallel growth in the expanding universe. Expansion acts like a brake that slows down the clustering. When we have a universe expansion, we want to talk about the Bremsstrahlung radiation. And this Bremsstrahlung is a radiation, and we also call it as a braking radiation. Braking, it's such as it's reducing the speed of the charged particle. Whenever we have a charged particle, and I call it as a CP, mostly as an electron, it's a minus electron, and it's traveling as anisotropic, suddenly collide to the neutral atom. It's a neutral, we have a neutral atom, and these neutral atoms mostly as a metal tube, for example, we call it as a metal tube. So it's a metal tube and it's such as a barrier. A discharged particle, mostly as a negative electron, is with a high speed colliding with a neutral atom, and this barrier is decelerating the speed of this charged particle as electron. And after that, when this speed, we have for example v as the speed of this electron, and here we have n divided by infinity. It means that the speed is too much low. And after that we have a radiation. This radiation is actually a very high energy, and this energy, it's actually calling X-ray or gamma ray. This X-ray or gamma ray is producing from the radio waves to the high energy, and this intensity, I mean that this intensity and the measuring of this high energy depends on the speed of the electron. It depends on the both side. The speed of this electron is there. I want to use the red color. The first things we it this high energy depends on it's the velocity of the this charged particle as electron. Another things, and the second reason is that we have this metal, and we are considering the atomic actually number. So this atomic number and this velocity is very important to produce the radiation, which is calling the Bremsstrahlung radiation. So this application in this planet is medical imaging, radiation therapy, and nuclear safety. So in this process, as you are watching, the electron is losing the kinetic energy. So we all know that the energy is such as that we have a E is equal to E car. This car is a kinetic energy plus air potential. It's the potential energy. So it's losing the kinetic energy, and it's radiating its energy is converting kinetic energy to the high radiation and high energy. And this high energy it's maybe X-ray or gamma ray. So back to the literature. This expansion, I wanted to connect this one to the Hubble expansion, and these things that I wanted to talk about the expanding the universe expansion acts. So the first we had a cosmic microwave background or CMB, and this was the isotropic, and it was the seeds of the galaxies. And now we are talking about the Bremsstrahlung radiation, which comes from these sort of photons as the charged particles was scattering. One of them is scattering from one direction as the anisotropic, and it's suddenly collide with a neutral metal, and it's producing the breaking radiation. So after that, this high energy is making some things, and this is related to the universe expansion. For completeness, we can also consider the dark matter fluid in radiation dominated epoch described by Hubble expansion is equal to 1 divided by 2t. In this case, one can show that equation 1.14 loses both the nu to the power of 2 cot to the power of 2 delta cot divided by r to the power of 2 term, because nu is equal to 0 for the dark matter fluid, and the 4pg rho is 0 delta cot term, because the relevant delta cot would be the one of the radiation, which however doesn't cluster and therefore doesn't source perturbations in the gravitational potential. Equation 1.14 therefore reduces to the second derivative of delta cup based on the time 1 divided by t multiplied by derivative delta cup based on the time is equal to 0, giving the delta cup is almost equals to ln t. ln is something that the logarithmic based on the Neper number t plus a constant variable. Hence, dark matter perturbations grow only logarithmically during radiation domination. Similar computations show that dark matter doesn't cluster efficiently when the universe is dominated by the vacuum energy or by curvature. In summary, the standard history of structure formation is as follows. The universe became matter dominated when the scale factors was equation was almost equal to 1 divided by 3,400. At that point, primordial dark matter in homogeneities delta chi is almost equal to 10 to the power of minus 5 began to grow as t to the power of 2 divided by 3 almost equal to on length scales 1 divided by chi, which are 3,400 times smaller than the present horizon. Larger length scales started clustering later as soon as they become smaller. than the expanding horizon. During matter domination, a mode car re-entered the horizon when the scale factor was ica was almost equal to h0 to the power of 2 divided by k to the power of 2 up to the omicron 1 factors. This result follows from imposing k divided by ica is equal to h ica is equal to h0 square root omega m divided by I chi to the power of 3. At present time, we then have delta chi is equal to 10 to the power of minus 5 multiplied by R0 divided by I chi is equal to 10 to the power of minus 5 multiplied by chi divided by H0 to the power of 2, which is larger than unity on scales. H0 divided by chi is less than 10 to the power of minus 5 divided by 2, about 3 orders of magnitude smaller than the current horizon. No matter, in contrast, couldn't cluster because it was tightly coupled by electromagnetism to photons and was forming pressure waves. Later in the evolution of the universe, at all the combination was almost equal to 1 divided by 1100. The temperature became low enough and the photon mass diluted enough that electrons and positrons could bind to form neutral hydrogen. At that point, normal matter decoupled from the radiation and began falling into the gravitational potential wells that dark matter had already started to form. In this sense, dark matter is a key ingredient in the construction of the cosmic scaffolding observed in the universe. The observed matter power spectrum pk or equivalently the variance delta to the power of 2 corroborate this history. If the universe contained baryonic matter-only perturbations, would have had a much smaller power and would have exhibited much more pronounced oscillations. Bottom right panel of figure 1.5. In clear disagreement, the observations. A universe containing the right mix of baryons and dark matter, for example, in the proportions given in equation 1.1, agrees with data. The power spectrum change slope at chi is greater than 3400 omega radians. H0 almost equal to 10 to the power of minus 2 divided by MPC corresponding to scale entering the horizon at matter radiation equality and therefore undergoing the growth during matter domination. On top of the smooth function, the small vgls around chi is equal to 0.1 h mpc to the power of minus 1 called baryonic acoustic oscillations or BAO are the imprints of pressure waves due to the subdominant population baryons. As an aside, an important lesson of the above formalisms that dark matter made of objects with sizable speed nu wouldn't be described by nu is equal to 0 and minus rather it would diffuse suppressing the small scale inhomogeneities. Observational data therefore constrain the dark matter temperature equivalently the average kinetic energy of dark matter to be much smaller than the dark matter mass for thermalized particles. This means M is greater than the electron wall as discussed in section 3.3.1. So we are watching to the figure 1.6 which is illustrating result from a full sky and body dark matter simulations from the Potter and his colleagues based on the reference 22. So the next chapter would be 1.3.2 nonlinear growth of inhomogeneities numerical simulations. The previous subsection discussed analytically how pyramidal density perturbations grow delta chi grow due to gravitational attraction. The perturbative limit delta chi is too much less than 1 over densities eventually reach delta chi is almost equal to 1 so that the perturbative computation no longer applies. At this point, gravitationally bound systems start to form galactic subhalos, galaxies, clusters of galaxies, and etc. Smaller structures form refers in homogeneities, delta-T and larger at smaller scales, 1 divided by cos C above, larger structures from accretion of diffuse dark matter and from merging of pre-existing smaller structures. This process is referred to as a hierarchical structure formation. The dynamic of the growth is still described by the gravitational collision less Boltzmann equation retain the Eulerian form in equation 1.6, but now the nonlinear effects become relevant. The study of the evolution of inhomogeneities beyond delta equation almost equal to 1 is therefore done via computer simulations based on the reference 22. These are a remarkable feat as they are able to cover huge ranges about 10 to the power of 13 years in time from initial conditions at Z almost equal to 100 T almost equal to 10 mega years to Z is equal to 0 today and almost equal to 7 orders of magnitude in space. Some recent simulations deal with volume of Omicron 10 gigapc to the power of 3 with copies the resolution and equal to 11 orders of magnitude in density contrast from the delta chi is almost equal to 10 to the power of minus 5 or recombination to chi's delta chi almost equal to 10 to the power of 6. The typical density contrast in collapse large scale structures today and up to about 30 orders of magnitude in mass. The recent simulations by Wang and his colleagues in 2020 based on the reference 22 are able to resolve the same time Earth's mass hollows about the 10 to the power of minus 6 and cluster mass hollows 10 to the power of 14 and they can trace 10 to the power of minus 11 elements within a total simulated mass of 10 to the power of 19 thanks to multi-zoom techniques. What is done in practice is to simulate the gravitational motion of a large number n of massive points, hence the name n by the simulations moving in the expanding background of the universe, starting from typical realizations of the primordial inhomogeneities. Present computers can solve Newtonian equations of motion for n is equal to 10 to the power of 12 massive points, while elementary dark matter particles are much more numerous. Thanks to the universal nature of gravity, this is enough to simulate properly the physics on scales bigger than the size of single elements, where the mass of each element is m divided by n, with m the total mass in the computed volume. At the qualitative level, such simulations produce images and movies that show how dark matter clusters into filaments, walls, and pancakes that merge into hollows separated by voids, producing what is often referred to as a cosmic web. See figure 1.6. So here we have two different footnotes. The density of forming structures is roughly given by the cosmological density at the formation time. Therefore, small structures have higher density in agreement with figure 3.1. And the next footnote is that the approximation based on multi-poles and dedicated techniques allow the reduction of their n to the power 2 gravitational forces computation to an omicron n numerical complexity. Furthermore, the gravitational forces are softened on small scales to avoid unphysical scattering among nearby particles due to numerical issues. The simulations are performed assuming periodic boundary conditions. So, for instance, they show how objects with total mass 10 to the power of 12, such as the Milky Way, mostly form at a redshift z is equal to almost 1, while presently about 20% of the dark matter remains diffuse. At the quantitative level, simulations allow to predict the statistical properties of the formed structures. This distribution in mass, the hollow mass function, the typical shape is spherical or ellipsoidal. The typical density provides a rho r, the dark matter velocity distribution, and its variance sigma to the power of 2r. We will return to these quantities when discussing detailed results about the dark matter distribution in section 2.1.3 and 2.2 and possible anomalies in section 8.5. The claim here is more general. The dark matter hypothesis leads to an overall agreement between the qualitatives and quantitatives results of these simulations and observe properties of the large-scale structure in the current universe. As hinted to source time already, dark matter is a scaffolding that shapes and supports the distribution of the visible matter in the universe. Numerical simulations are instrumental in testing its presence because they provide the essential link between the theoretical models for the original evolution of cosmological structure and the actual astronomical observations. The discussion so far has concerned dark matter-only numerical simulations performed since the 1980s. Ordinary matter, aka baryons, is less abundant than dark matter, but its effects are very important and should be included, which is what recent simulations called baryonic or hydrodynamical simulations started to do, trying to achieve precision based on the reference 23, discussing in detail how these simulations model baryons and their interactions goes beyond the focus of our review. In general terms, these simulations need to take into account a large number of different physical processes on different time scales and for very large range of velocities, densities, temperatures, viscosities, and etc. and other sort of features. The ingredients include gas, hydrodynamic, gas cooling, and radiation magnetic fields. Since these significantly contribute to the pressure, their amplification included in the computer codes presumably makes their more complicated seeds irrelevant. Star formation and star death, as well as dynamics of stellar ejecting, including supernova. It's when the star is dying, and it is the stellar ejection. Stellar ejection is that when the star is ejecting its mass, and it's called as a mass ejection, and mostly it's started from the hydrogen, which, as I described it former, is some sort of the first element. It is the first element in the periodic table or Mendeleev table when the proton and electron finally make a decision to combine and make a neutral hydrogen. So when the star is dying, it's ejecting its mass, and this is calling as some sort of stellar ejection, including supernova. The resultant cosmic rays contribute to pressure in the interstellar medium and significantly change the gravitational potential by the moving matter from the localized center to the wide surrounding region within a short time scale. It means that in a very short time scale, this mass and they are very dense, come from the core of the star, and by the aid of the pressure, they are pouring to the outside and outside of the star. Supermassive black holes, personally massive galaxies, their seeds are not known. They presumably grow acquiring gas with possible mergers, and etc. Dust, thermal conduction, and viscosity are believed to be less important. As a result, the computer codes recently started to produce realistic galaxies, while the details vary. For example, the formation of spirals critically depends on how stellar feedback regulates star formations. Different codes presently seem to agree on a number of predictions. The overall conclusion seems to be that the LCDM model, including baryons, can account for galaxy formation, and that the basic physics that shapes galaxies has been identified. Such codes do contain, however, free adjustable parameters, including those that control the numerical approximation, such as the spatial resolution and the modeling of the so-called subgrid physics. As such, there is a usual danger for possibly overfitting data to the incomplete or even incorrect correct models where adjusting the phenomenological parameters may mimic the effects of something else. Numerical simulations are single dark energy, at least in the form of an accelerated expansion of the underlying universe, hence entering in the background Hubble parameter at late times. Alternative models of dark energy are also simulated. The effect on structure formation can be sizable, but it is not always easy to disentangle it from other degenerate effects. Finally, we mentioned that the numerical simulations can be used to study the nature of dark matter, for example, to explore the deviations from the assumption of vanilla cold collisionless dark matter. For instance, numerical simulations of warm dark matter, self-interacting dark matter, and fuzzy dark matter, which is between the warm and cold dark matter, with orbital baryons have been performed in the reference 25. We will come back to some of the constraints imposed by these simulations in section 2.3 and 2.4. In this context, a powerful tool in the ethos framework based on the reference 26 ethos, or the effective theory of structure formation, is a scheme in which the different microphysical dark matter interactions are translated into general effective parameters that modify the perturbation equations discussed in section 1.3.1. Hence, in principle, performing one ethos or effective theory of structure formation numerical simulation with a chosen set of the effective parameters allows to constrain all the microphysical models captured by such a set. So thank you so much for watching my tutorial video until the end. Today is the 14th of the August, and I described the two important things to you that I want to make them besides together, and you can understand them too much better because they are not very separated from each other. The first is that how the universe shaped, and we come from the cosmic microwave background in almost 380,000 years ago. Universe was too much hot and dense plasma. After that cooling and time passing, the proton and electron combined and made a neutral hydrogen. And at this time, the universe at the first time was just photons and scattering charged particle to all of the direction. It was the isotropic. Isotropic is equal to all the ways. After that, we are reaching that how this is the seeds of the galaxies. After that, we are coming to the Bremsstrahlung, or breaking radiation, when the charged particle with the velocity collide to the neutral metals or neutral atom, and this velocity is diminishing from this velocity to the this velocity divided by infinite, which is very low. So it's producing the high energy, and this high energy is such as the X-ray or gamma ray, and this X-ray or gamma ray intensity as a high energy, it is depending to the first initiating of the velocity of the charged particle, and also the atomic number in the other sides. So thank you so much for watching my tutorial video. Today is the 14th day of the August 2026. If there is any simulations for this literature, you can find it from my github.com/masterscript, github.com/HashiScript, and github.com/SaffroScript. So tonight I want to summarize my lecture. That was including the two separate important things: cosmic microwaves and Bremsstrahlung or breaking radiation. Cosmic microwaves is a photons that is isotropically scattering to the universe and made the seeds for universe. And Bremsstrahlung is a total energy that we have energy of kinetic energy and potential energy. And this charged particle, when they are traveling to the space as anisotropic. Anisotropic is one directional with a velocity of v, and colliding to the metal and decreasing the velocity and making the high energy, and losing the kinetic energy. So these two important phrase or concept, I described it tonight. And if there's any simulation for Bremsstrahlung or breaking radiation or cosmic microwave background, you can find it from my GitHub's address.